Hello everyone and welcome back to another video. Today we're going to talk about solving radical equations. Now in previous grades we've talked about linear equations such as 2x minus 1 is equal to 4. And the idea behind this was to figure out what values of x can go into this equation to make the left-hand side equal to the right-hand side. So in order to solve this, we would add 1 to both sides and we'd have 2x is equal to 5, and then we're going to divide both sides by 2. And we end up with something like x is equal to 5 over 2, or 2.5. Now the way that we would verify this is by plugging this 2.5 or this 5 over 2 back into our original equation. So this means that we would have 2 times 2.5 minus 1 is equal to 4. 2 times 2.5 gives me 5. 5 minus 1 has to equal to 4. So 4 is equal to 4. And we have verified our solution. So in grade 11, we're now going to introduce the idea of radicals into such equations. So typically with these types of equations, there's going to be 3 main steps. Step number 1, we're going to look for some restrictions. Step number 2, well, number 2 really should be to solve. And then step number 3, we're going to check our solutions afterwards. Okay, so if you've forgotten what restrictions are, let's take a look at a quick example before we actually figure out how to write our restrictions down. So the reason why we have restrictions when it comes to radicals, let's look at an example such as the square root of x minus 1. So a really straightforward example, and maybe I'll put that in brackets. So square root of x minus 1. And let's go ahead and graph this. And we can see here that our graph doesn't extend all the way down this way. In fact, it actually stops at a certain point. So I'm going to go ahead and look for our intercept there. And it stops when x is equal to 1. And there's nothing less than when x is equal to 1 here. So we can see that our domain has a restriction there. Let's do the same thing with a different value. Let's go ahead and go back. Let's go with the square root of, let's say, let's go with something such as x minus 2. And we can already see here that we could guess that it ends, or it starts, depending on how you look at it, right here when x is equal to 2. So there's nothing less than positive 2 in this case. So when we're looking at our restrictions, basically we're trying to figure out what our values of x are that actually give us some real numbers when we plug those x values into here. So once again, if we're looking for some numbers, let's say, for example, if we said x is equal to 1 in this case, well, 1 minus 2 gives us negative 1. But we've already learned previously that we can't take the square root of negative numbers. So putting x equals to 1 here simply would not work. If we put 2 into here, 2 minus 2, well, the square root of 0 is just 0. So when x is 2, then y is equal to 0. So that works perfectly fine. And that's going to be essentially our minimum value. So going back to our idea of restrictions here, if we look at the square root of x minus 2, really we're trying to make sure that whatever's on the inside of whatever radicals we're looking at, whatever is on the inside has to be greater than or equal to 0. So anything under a square root sign has to be positive or 0, essentially, is what we're saying. So to solve for x here, we're gonna add 2 to both sides. So then we just end up with the restriction that x has to be greater than or equal to 2. So again, looking back at our graph here, we can see that this is true, that x has to be greater than or equal to 2 in this case for us to actually have some corresponding outputs on our graph. So to summarize, really we're saying that whatever our radicand is, and remember this stuff underneath the radical sign, your radicand essentially just has to be greater than or equal to 0 when it comes to looking for your restrictions. Coming back to step number 3 here, again, we're going to work through some examples together. We need to look for something called extraneous roots, and these are going to be really important. I won't spend too much time talking about them right now, but really extraneous roots are really just any answers or solutions that don't satisfy the original equation. So keep that in mind. We're going to work through some problems first before we come back to that. So taking a look at some equations of just one radical term, there's going to be a few different variations that we might run into. So looking at this first one, we're going to keep in mind that our goal is to get x on its own at some point. So maybe even before we just start, we're going to look at our restrictions first. So we're looking at anything underneath our radical signs, and again, since we only have x as our radicand, our restriction is pretty straightforward. We just have x has to be greater than or equal to 0. So that's going to be our restriction. So you can go ahead and state that. Our restriction is x has to be greater than or equal to 0. It cannot be a negative number. So starting off with our equation, step number 1, what we're going to do is we're going to try to group all of our like terms. So in this case, we have some like radicals here. So I'm going to subtract 2 root x from both sides. So this leaves me with root x minus 4 is equal to positive 1. My next step here, I want to try to get this radical by itself, so I can add 4 to both sides, so plus 4 and plus 4. And I'll end up with the square root of x is equal to 5. My last step here is to square both sides because I don't want the square root of x, I want just x. So in order to get x, I'm going to square both sides. And we'll end up with x is equal to 25. So that is what my my current solution is. But we want to make sure that we verify to make sure that this is correct. So let's go ahead and verify by plugging in this 25 back into our original equation. So we'll have 3 times the square root of 25 minus 4 has to equal to 2 times the square root of 25 plus 1. So all I've done here was instead of having an x in my equation, I'm just going to put that 25 back in there. So this means I have 3 times 5 minus 4 has to equal to 2 times 5 plus 1. So this means I have 15 minus 4 is equal to 10 plus 1. So here on the left-hand side, I get 11. And here on the right-hand side, I get 11. So I get the left-hand side is equal to the right-hand side. So that should say LHS. So left-hand side is equal to the right-hand side. Therefore, we have confirmed or we verified our solution to this problem. In example number 2 here, once again, with our radical, let's go ahead and figure out what that restriction is going to be. So whatever's underneath that radical sign has to be greater than or equal to 0. So 2x minus 1 has to be greater than or equal to 0. And let's add 1 to both sides. So plus 1 and plus 1. And we'll get 2x has to be greater than or equal to 1. And then divide both sides by 2. So for my restriction, I get x has to be greater than or equal to 1/2. That is my restriction. So we can go ahead and write that down. Our restriction is right there. And from here, we can go ahead and solve it. So right here, we've got a radical. And remember, our goal is to isolate it or get it by itself on one side. So my first step here is going to be subtracting 5 from both sides. So what that allows me to do is to get this radical on its own. And I'll have the square root of 2x minus 1 is equal to -3. At this point, we're going to square both sides so I can get that x out from underneath the radical sign. And we'll end up with 2x minus 1. So once I square that radical sign, once I square the square root, I just basically release that 2x minus 1. Over here on the right-hand side, just keep in mind that this is the same thing as -3 times -3, which gives me a +9. We add 1 to both sides. And we'll end up with 2x is equal to 10. Divide both sides by 2. And we get x is equal to 5. So let's verify our solution. And we're going to plug this 5 back into our original equation. So we have the square root of 2 times 5 minus 1 plus 5 has to equal to 2. 2 times 5 gives us 10, and 10 minus 1 gives us 9. So I get the square root of 9 plus 5 is equal to 2. So that's 3 plus 5 is equal to 2. 8 does not equal to 2. So the left-hand side does not equal to the right-hand side. Therefore, we can state that x equals to 5 is not a solution. So this is what we'd call an extraneous root. So x equals 5 is an extraneous root. So coming back to the idea of what an extraneous root is, we ended up with an answer that doesn't actually work. Well, why is that? Taking a look at a really quick example, let's say we have x is equal to 3. So we know for sure that x is equal to 3. Let's imagine if we square both sides. So let's square the left-hand side and we square the right-hand side. And we'll end up with x squared is equal to 9. So in this case, we actually have two solutions that can satisfy this equation. Something squared gives us 9. So from here, we know that 3 squared gives us 9, and negative 3 squared is equal to 9. So from here, we actually have two solutions that satisfies this equation, but we know for sure that this answer of negative 3, right? So if we said here that we have two solutions, x is equal to 3 and x is equal to negative 3, we have to reject this answer because of the fact that our original was just simply x is equal to 3. So the takeaway from this is that anytime we square both sides of an equation, we inherently get an extra answer that may or may not work in our original equation. All right. So while squaring doesn't necessarily mean for sure you will have extraneous roots, it's always a good idea to double check by verifying all of your answers. Looking at some radical equations with two radicals in them, we're going to look at how our restrictions could potentially change just a little bit. So in this first example, we're going to start off with our restrictions. So from this guy right here, x minus 1, we have x minus 1 has to be greater than or equal to 0. Once we add 1 to both sides, we get x is greater than or equal to 1. So that's one restriction that we have. And then from the second radical, we have 2x. Maybe I'll do this in black. 2x plus 3 has to be greater than or equal to 0. Let's subtract 3 from both sides. And then we're going to divide both sides by 2. So x has to be greater than or equal to negative 3 over 2. So now we have two sets of restrictions, and we want to figure out, well, what does this mean for us? How does this work out? The simplest way to visualize this is by using a number line. So let's go ahead and do that. Let's start off with a 0 here. Let's go with a 1. We'll have a negative 1. And then we're going to plot both of our restrictions. So we have x is equal to 1, essentially just saying, starting right here. So x has to be greater than or equal to 1. So we have a solid point right there, and we can basically continue to go past this way. Now with this negative 3 over 2, and maybe what I'll do is I'll do this in blue actually, just so we can get an idea of where it is. X is greater than or equal to negative 3 over 2. So negative 3 over 2 is negative 1.5. So we're looking right here, negative 1.5. And we're going to go ahead and essentially just draw our line over this one. We can see that it overlaps a little bit. So the idea behind this is to figure out, well, which restriction actually covers enough so that our equation actually works. Well, let's think about it this way. if I put a 0 into both of my radicals here, do they both still work? So 0 is part of the blue restriction. So if we look here, 0, let's start with this one right here, 2 times 0 plus 3. So we have 2 times 0, which is 0, 0 plus 3. That gives me the square root of 3. That works out fine. But on the other hand, if I put 0 into the first radical here, we'd end up with the square root of 0 minus 1. That would be the square root of negative 1. And that absolutely does not work. So what we're going to do is we essentially just go with whatever is overlapping here. So looking at our number line again, we're going to take this original red restriction and we're going to work with this as our restriction, because this one simply does not cover enough to have it work with whatever radicals are in our equation. So our primary restriction is going to be that x is greater than or equal to 1, and that's the one that we're going to roll with here. So just going ahead and rewriting our equation so we have a little bit more room. We have the square root of x minus 1 and the square root of 2x plus 3. Let's square both sides. So I'm going to square the left-hand side, and I will also square the right-hand side. So I've squared both sides here, and that will leave me with x minus 1 on the left-hand side and 2x plus 3 on the right-hand side. So I'm going to isolate for my x on one side by adding 1 to both sides first. So we'll have x is equal to 2x plus 4. Then let's subtract 2x from both sides. And we'll have negative x is equal to positive 4. We can multiply both sides by negative 1, and we get x is equal to negative 4. So let's go ahead and verify our answer here by plugging that negative 4 back into our original equation. So we get negative 4 minus 1 is equal to the square root of 2 times negative 4 plus 3. Over here we'll have the square root of negative 5 is equal to the square root of negative 8 plus 3. So the square root of negative 5 is equal to the square root of negative 5. So if you haven't already noticed, we just took the square root of a negative 5 on both sides. It's not possible on the left-hand side, and it's also not possible on the right-hand side. So even though we have the same value, these values don't actually work. They're not real numbers. We can't take the square root of negative 5. So we actually have no solution here. So we have no solution, otherwise known as an extraneous root. This does not work out. Now, going back to our idea of restrictions, if you caught it earlier, well, we have x is equal to negative 4. When we compare this to our original restriction, we said that x has to be greater than or equal to positive 1. And we can already see, even before we verify, that this simply does not work. So x equals negative 4 has to be nixed. That's not our solution. In this next example, we start off again with our restrictions. So we get something pretty similar to our first set. So from here, we get x right there. X has to be greater than or equal to 0. From the second radical, we end up with 2x plus 1 has to be greater than or equal to 0. 2x has to be greater than or equal to negative 1. We've subtracted 1 from both sides. And finally, divide both sides by 2. So we get x has to be greater than or equal to negative 1/2. So once again, to figure out which one is our primary restriction, let's draw a number line here. So I have 0, which is going to be right there, and negative 1/2. So essentially, we're looking for whatever's going to be overlapping. So here for negative 1/2, we've got this going through just like so. And then for x has to be greater than or equal to 0, that's the blue line. Basically, we're looking for that part that overlaps, and it overlaps when x is greater than or equal to 0. So that's going to be our primary restriction. So continuing on with our original equation, let's go ahead and rewrite it down here. Square root of x plus 5 is equal to the square root of 2x plus 1. In this situation, we can't really simplify it more than we already have, or rather we can't really isolate much except for this 2x plus 1. Typically, it's a lot simpler if we isolate for the more complex radical. So you can see here 2x plus 1 is more complex than the square root of x. So it's good that that's already isolated. What we're going to need to do here is to square both sides. Once again, to try to get rid of as many radicals as we can. But in doing so, essentially what's happening on the left-hand side is we have square root of x plus 5 times the square root of x plus 5. And over on the right-hand side, since we squared a square root, we will now end up with 2x plus 1. It comes out from underneath the radical sign. And now we can use the distributive property to multiply our binomials together. So square root of x times square root of x just gives us x. And square root of x times 5 gives me plus 5 square root x. Moving on, we've got 5 times root x gives me plus 5 root x. And then 5 times 5 gives me 25. So plus 25. And that equals to the 2x plus 1 that's still on the right-hand side. We can group together our like radicals. So x plus 10 root x plus 25 is equal to 2x plus 1. Since we still have a radical in our equation here, we're going to once again try to isolate it by moving everything else from the left-hand side over to the right-hand side. So I'm going to subtract x, and I'm also going to subtract 25 from both sides. This leaves me with 10 square root x on the left-hand side. 2x minus x gives me x, and 1 minus 25 gives me minus 24. Now we end up with 10 square root x is equal to x minus 24. Now, in some cases, it might be a little bit easier to divide whatever coefficient we have here. So what that means is, let's say this wasn't a 10, this was a 2, and we had a 2x here. We can actually just divide everything here by 2, and we'd end up with square root x is equal to x minus 12. And that would be fantastic, if we ended up with the correct coefficients. But since we don't have them, we have to do something slightly different, but not really that complicated either. We're going to square, once again, both sides, so the left-hand side and the right-hand side. And essentially what this means is that we have 10 root x times 10 root x, and that's going to be equal to x minus 24 times x minus 24. Over here on the left-hand side, we have 10 times 10 gives me 100. And the square root of x times the square root of x just leaves me with x. On the right-hand side, let's go ahead and multiply x times x gives me x squared. X times negative 24 gives me minus 24x. Negative 24 times x gives me negative 24x. And then 24 times 24, or negative 24 times negative 24, gives me plus 576. So let's clean up the right-hand side a little bit. We can subtract those like terms. That gives me minus 48x plus 576. And then we can subtract 100x from both sides. And now on the left-hand side, we have 0 is equal to x squared minus 148x plus 576. Now, even though this is a simple trinomial where a is equal to 1, we have some pretty big numbers, and I don't feel like factoring something with such big numbers. So we're going to use the handy-dandy quadratic formula to help us out. So before we get started, we know that a is equal to 1, b is equal to negative 148, and c is equal to 576. So our formula, or our quadratic formula, was x is equal to negative b plus or minus the square root of b squared minus 4 times a times c divided by 2 times a. So we'll have negative 148 plus or minus the square root of negative 148 squared minus 4 times 1 times 576. And that's all divided by 2 times 1. So once you plug everything in and simplify a little bit, negative 148 gives me a positive 148. We'll have plus or minus. And once we simplify all of this stuff on the inside, negative 148 squared minus 4 times 1 times 576. This actually equals to the square root of 19,600. And that's going to give us a nice square root actually. So we'll do that in the next step. And we're just going to divide everything by 2. So 148 plus or minus, and the square root of 19,600 happens to be a nice even 140. And we're going to divide everything by 2. And from here, we get 2 answers. And let me give myself a little bit more room here. We'll get answer number 1. So we'll get x is equal to 148 plus 140 divided by 2. And we end up with x is equal to 144. For solution number 2, we have x is equal to 148 minus 140 divided by 2. And we end up with x is equal to 4. Now, since we have 2 solutions, we're going to have to verify both times, or both of them. So let's go ahead and do so. So for the first answer, 144, let's go ahead and put that back into our original equation. So square root of 144 plus 5 has to equal to the square root of 2 times 144 plus 1. So the square root of 144 is 12, and 12 plus 5 then has to equal to the square root of 2 times 144, which is 288, and 288 plus 1 gives us the square root of 289. Well, luckily for us, the square root of 289 is just 17, and fortunately enough, 12 plus 5 also equals to 17, so the left-hand side is equal to the right-hand side. So x is equal to 144. X equal to 144 is a solution. And doing the same with the right-hand side, let's go ahead and plug in that value of 4. So we have the square root of 4 plus 5 has to equal to the square root of 2 times 4 plus 1. Remember, it's all underneath. The square root of 4 is 2. 2 plus 5 has to equal to 2 times 4, or the square root of 2 times 4, which is 8. 8 plus 1 is the square root of 9. So we get 7 is equal to 3. That is not true. 7 does not equal to 3. So the left-hand side does not equal to the right-hand side. Therefore, x is equal to 4 is extraneous. Extraneous. So this is not a solution. So for our last problem here, let's go ahead and find our restrictions first. So for our first restriction underneath this radical, x plus 3 has to be greater than or equal to 0. Let's subtract 3 from both sides. Oops, did not subtract 3. Let's subtract 3 from both sides. And we'll get x has to be greater than or equal to negative 3. For our second radical here, x plus 11, we know whatever is underneath there, x plus 11 has to be greater than or equal to 0. Let's subtract 11 from both sides, so x has to equal, or x has to be greater than or equal to negative 1. Once again, if we were to do a quick number line here, we'd see that negative 11 is over here, negative 3 is here. We could have the negative 11 coming across this way, but we can see that the overlapping portion actually starts off when x is greater than or equal to negative 3, meaning that this is our primary restriction. So jumping into our problem here, we can see that we have one radical isolated already, which is great for us. Again, it's really up to you which one you want to isolate. We could just subtract 2 from both sides and isolate the square root of x plus 3. but we'll just work with whatever we've got. So let's square both sides first. And this means that essentially we have the square root of x plus 3 plus 2. Since we squared it, we're going to go ahead and multiply it by itself again. So multiplied by the square root of x plus 3 plus 2 on the left-hand side. And now, since we have squared the right-hand side, that x plus 11 is freed from its radical prison. And we're going to use our distributive property to multiply these out. The square root of x plus 3 times the square root of x plus 3 is just simply x plus 3. And maybe I will do this in a different color just so we can keep track of what we're doing there. So the square root of x plus 3 times the square root of x plus 3 is just x plus 3. The square root of x plus 3 times 2 gives me plus 2 times the square root of x plus 3. And the same thing over here, 2 times the square root of x plus 3 gives me another plus 2 root x plus 3. And then finally, 2 times 2 is just 4. And this is equal to x plus 11. So let's add our like terms together. So we'll have x plus 3 plus 4 square root x plus 3 plus 4 is equal to x plus 11. Let's clean things up a little bit on the left-hand side here. So we know we've got an x on this side. Let's go ahead and subtract it from the right-hand side as well. And here we can see that we've got a plus 3 and a plus 4, so we're just going to go minus 7 from both sides. And we have 4 square root x plus 3 is now equal to, we said x minus x is 0, and 11 minus 7 is 4. So remember in the previous question, and maybe I'll kind of go back to it. Remember in this question here, I said if our coefficient here allows us to divide everything nicely on the left-hand side and the right-hand side, we can go ahead and do that. Well, nicely enough, for this question here, we can see that I have a coefficient of 4 on the left-hand side here, and I just have a 4 here. So what I can actually do is just divide both sides by 4. And now I'll have the square root of x plus 3 is equal to 1. Now again, what I could have done is I could have squared both sides, but again, why give yourself more work? So now things become a lot easier. We're going to square both sides at this point since our radical is now isolated. And we'll have x plus 3 is equal to 1. We can subtract 3 from both sides, and we get x is equal to negative 2. So that appears to be our solution, but we will always want to make sure we verify by plugging this into our original equation. So our original equation had the x plus 3 underneath, so we have the square root of negative 2 plus 3, and then plus 2 on the outside has to equal to the square root of negative 2 plus 11. And from here, we've got the square root of 1 plus 2 is equal to the square root of 9. The square root of 1 is just 1. 1 plus 2 is equal to 3. So we get 3 is equal to 3. So the left-hand side is, in fact, equal to the right-hand side. Therefore, x is equal to negative 2 is a solution to this equation. Now, one thing that we haven't talked about yet is, even though we verified this and we've gone through it, one other way that we can also verify that you've done everything correctly is by using your graphing calculator. So if we go back to, let's go to something with a nice solution here. Let's go to, maybe we'll go to, oh, we don't really have anything with really nice solutions. We can just stick with this one. Let's go to this one. So what's going to happen here is we're going to go to our graphing calculator. Let's get rid of what we had in here before. And I'm going to put y1, and I'll maybe write this down as well. My graphing calculator, we're going to go y1 is equal to the square root of x plus 3, making sure that we put our brackets in the right spot. So y1 is equal to that. y2 is equal to the square root of x plus 11. And maybe I'll put this in a different section. Let's go ahead and drag this all the way down. So, and we'll call this bonus. So bonus verify with calculator. And so we have the y1 and we have the y2. So what's going to happen here, and you can probably already guess, is we're going to be looking for the intersection. So let's go ahead and do this first. The square root of x plus 3. And then we're going to put the plus 2 on the outside. And then for my y2, the square root of x plus 11. Notice I'm putting my brackets here to ensure we get an accurate graph. And we can see that we have one kind of curved line here. This one's also going to be essentially a curve as well, but you can't really see it. And what we're looking for here is the intersection. So on my Casio, I've gone ahead and pressed Gsolve. On a TI calculator, you would go second, trace, and then intersection. And then that would give you your intersecting point, or intersect rather. So when you go intersect on either calculator, we can see here that we have our intersection when x is equal to -2, y is equal to -3. So for us, even if we try to find another solution here, we can only find the one. So essentially, like I said, if we're trying to verify, we're looking for the intersection. So we're going to look for the x value of the intersection. And that will help us confirm whether or not something is the correct answer. So let's try one more bonus question where we'll actually have two solutions that'll work for us. So we have square root of x minus 2 plus 3 is equal to the square root of 4x plus 1. So really quickly, we'll do our restrictions on the side. So for this first radical, we'll have x minus 2 is greater than or equal to 0. X is greater than or equal to 2. And then for this radical on the right-hand side, we have 4x plus 1 has to be greater than or equal to 0. So 4x has to be greater than or equal to -1, and x has to be greater than or equal to -1/4. So if we're looking at our number line here, we can see that -1/4 is probably about here, and +2 is here. So for our overlapping portion, our green kind of starts here, and we can see that our overlapping portion is the +2. So that's going to be our restriction for this equation. So getting us started, let's square both sides since our radical on the right-hand side is already isolated. And from here, we'll have the square root of x minus 2 plus 3 times the square root of x minus 2, rather. Square root of x minus 2 and then plus 3 is equal to just 4x plus 1 since we squared the square root, and that 4x plus 1 comes out. Square root of x minus 2 times the square root of x minus 2 gives me x minus 2. And then here we'll have plus 3 square root x minus 2, and then plus 3 square root x minus 2, and then plus 9 is equal to 4x plus 1. Let's combine our like terms here in the middle. So we'll have x minus 2 and then plus 6 root x minus 2, and then plus 9 is equal to 4x plus 1. Let's clean things up a little bit. Here we have minus 2 plus 9, which gives us plus 7. Let's subtract 7 from both sides. We're also going to subtract an x from both sides here. So this leaves me with 6 square root x minus 2 is equal to 3x minus 6 on the right-hand side. Unfortunately for us, this equation doesn't have nice coefficients for us to divide out very well. So what's going to happen is let's just go ahead and square both sides. And we'll end up with 36 times x minus 2 on the left-hand side. Once again, 6 times 6 gives me 36. And root x minus 2 times root x minus 2 just gives me x minus 2. On the right-hand side, I'm going to multiply this out through x minus 6 times 3x minus 6. That leaves me with 9x squared. I'll have negative 6 times 3x gives me negative 18x. I'm going to do that twice. And then negative 6 times negative 6 gives me plus 36. Over on the left-hand side, 36 times x gives me negative, or 36x rather. And then 36 times negative 2 gives me negative 72. I can clean things up on the right-hand side here by subtracting those together. So minus 36x and then plus 36. I'm going to move everything from the left-hand side to the right-hand side. So I'm going to subtract 36x and then I'm going to add 72. So this means I have 9x squared minus 72x. And 72, or 36 plus 72, that gives me plus 108. So the nice thing about this equation is I can divide everything by 9. So 9x squared divided by 9 gives me x squared. Negative 72x divided by 9 gives me negative 8x. And then 108 divided by 9 gives me positive 12. That means I can factor this as x minus 6 times x minus 2. So therefore, I will have two solutions. So again, from our quadratic equations outcome, we know that x is equal, or maybe I won't skip that step, x minus 6 has to equal to 0, so x is equal to 6. That's one solution. And then over here, x minus 2 is equal to 0, so x is equal to 2. That's my other potential solution. So let's go ahead and verify. So I have two different sections to verify. So we're going to plug these back into our original equation. I've already forgotten it at this point. So I have square root of 6 minus 2 plus 3 has to equal to the square root of 4 times 6 plus 1. And let me double check that. Yep, we're good to go. So this means that I have the square root of 4 plus 3 has to equal to the square root of 25. So that gives me 2 plus 3 is equal to 5. So I get 5 is equal to 5. The left-hand side is equal to the right-hand side. So we are good to go with this guy. So that's perfectly fine. And let's check out the solution of x is equal to 2. So once again, we have 2 minus 2 underneath plus 3 is equal to 4 times 2 plus 1. So this gives me the square root of 0 plus 3. And this is equal to the square root of 9. 3 is equal to 3. So the left-hand side is, in fact, equal to the right-hand side. So x is equal to 2 is also a solution. Now let's go back to our kind of bonus method of verifying. So we've done it algebraically. Now let's go ahead and try it graphically. So we're going to put this first, or this left-hand side into y1 and this right-hand side into y2. So in our graphing calculator, let's put the square root of x minus 2 and then plus 3. And then now we have, oops, let's get out of that. The square root of 4x plus 1. Let's go ahead and graph this. We're going to draw this. And we know that it's going to be a little bit tricky. So depending on your window settings, you might need to change things up a little bit. What I can do here is I'm actually going to just kind of focus in a little bit on that top right quadrant. So I'm going to go to -2 only. Let's go until 10. And let's start at, oops, let's go down a little bit. Let's go from 0 to 10. And this should help us kind of see exactly where there might be an intersection. So we can see that there's one here for sure as this line kind of overlaps there. And we see another potential intersecting point right there. So I'm going to hit G-solve. I'm going to look for my intersection. So my first one here, I can see x is equal to 2. And if we look at our answer again, we have x equals to 2. So y is equal to 3 when that happens. And if I press right on the Casio, we can see that we have a second intersecting point where x is equal to 6. So again, using your calculator, it's an extremely powerful tool when you understand how to use it. This is another really good way for you to verify your answers. Even though we've already done it algebraically, just having that graphical visualization can really help you double check, triple check your answers. So that brings us to the end of today's video. Hopefully you learned a thing or two. Once again, if you have any questions or concerns, feel free to leave them in the comment section below. Thanks again for watching, and I hope to see you in the next video.